I come from more of an engineering background, but networks has been a theme that's always fascinated me. And I truly think if we look at a system like close enough, there's a genuine networks question that arises from each context. To put some of the directions that I've worked in context, I'll just start by saying what are different contexts in which I have looked at networks, and in particular, what are the nodes and edges. So, broadly speaking, there are three broad areas in which in which I've looked at networks. So, first is in the context of distributed systems. You can think of these as a network of mobile devices, a network of sensors, and so on. Uh, the other is something that I'm working on more recently. It goes by many names. Sometimes people call them Markov random fields, probabilistic graphical models, directed versions of them are called Bayesian networks. They're essentially, the idea is that the edge, so the nodes are a collection of random variables, and edges or in general other combinatorial objects encode conditional dependencies in your observation. And the third one, which is I think there were so many talks around this theme, is more around the context of social networks, social systems, and contact processes where there's the edge is a pathway for contagion to travel between people. And you can ask many different questions in all of these contexts. The types of questions that I have looked at in the first thread, it's been actually a network design problem. So here, and this is what I'm going to focus on primarily today. Here, as you will see in this talk, the notion of a random graph or a probabilistic rule to construct a network is actually a design choice that an engineer can make. So there is a very direct connection between some of the distributed algorithms and random graphs. And the other thrust, I'll not speak about too much, just briefly allude to them. The second is around learning from observational data, where you're trying to encode dependencies as graphs. And what this representation helps us is trying to come up with computationally often more efficient ways to learn. And finally, in the context of studying contact processes on networks, when the pandemic was happening, I looked at trying to model if you have a contagion that as it propagates in the network, there is some chance, some structure around if it could mutate, what would be the epidemic characteristics. These are some of the works that I've done on this. And today, I'm going to mostly focus on this first thrust. And just to sort of put my talk title in context, so here structure will come up as various notions of connectivity. And there will be this theme of efficiency in terms of if you're in like a setting like a collection of mobile devices, you want to have utility and be able to do useful things in the network without having to communicate too much. There's also a notion of computation as efficiency, is how much computing you need to expend to learn. And throughout, I'll also allude a little bit to various modes of heterogeneity that come up in these contexts. And I would like to acknowledge all of my collaborators. And for today's talk, most of the work is in collaboration with Osman and Jan. All right, so here is a broad outline of my talk. And in addition to this, given the audience and so one of the things that I've loved about this campus is the density of chalkboards. So towards the end, I will actually try to talk about some questions that will be interesting and that will be on the board. So let me dive into this. So just to put it in perspective, so I will now make this, I've been very vague about saying that there is a random graph question embedded in distributed systems. So I'll make that concrete. And in particular, so there are, I think, many notions of expansion and balancing sparsity if you think of the number edges and connectivity. In these contexts, people sometimes try to find methods in which you can get connectivity, different notions of connectivity without expending too many edges, while allowing for a very simple distributed way to construct the network. And towards this, I will introduce random layout graphs, which has been an object, I think, for more than four decades. It's been in the random graph literature, comes up in various names, including random M-orientable graphs. And it's often hidden in a lot of these systems. And then I'll talk about some of the properties that are known about this, and then some other properties that, based on the context we looked at, were interesting to study. and then what we studied, and I'll conclude with on the board some further properties that would be good for the settings I'll describe. Okay, so now we are in this regime. I'll use toy illustrations for networks. Nodes are now our devices or reservoirs of data. And the edge will be a notion of a secure communication channel. So let me make this more concrete. If at any point you have any questions, let me know. I'm abstracting out a lot of the details of the system to illustrate the key points. So suppose following is the setting. We are given a graph and we have all nodes on this graph that hold some private values. You can think of these as something simple as like maybe you want to learn everyone's like average opinion, or you could also think of this in the context of those who look at neural networks and training neural networks. These could be gradients that nodes compute locally at their based on the data they have. And then the edge here is the presence of a secure communication channel. I'm abstracting out how that might be constructed, but there's many ways to do that. And then there is no real central authority trying to orchestrate how, for instance, if the goal is to learn just the aggregate sum or average, there's no one orchestrating that process. And this is something that is a problem that's well studied in the privacy and cryptography literature going back to the 80s, where they have a very simple idea. So what they say is each pair of nodes that are neighbors on this graph, what they'll do is they'll compute a mask. One of them will add it to their private value. One of them will subtract it, and they will broadcast this on the network. So for instance, if Rajat and I were neighbors on this graph, we will, first of all, using some cryptographic keys, or it could be also some other private mechanisms, we will agree to a shared value that you will add to whatever you share with the network, and I will subtract from it. And then the hope is they cancel in aggregate. So just going back, so this was something that was well studied long back. There were several innovations that came up over the last decade when people tried to look at situations where these weights could be really, really high dimensional, such as when you are training neural networks and you have gradients. And then the other thing is there could be lots of nodes and devices that come and go, and they could drop out. So you could imagine if lots of nodes dropped out, their masks wouldn't get cancelled. So there are ways in which people have innovated to make sure that you get utility in that. Okay. But for the purposes of our talk, all we have to remember, we're given a graph. Everyone has a private value. Our goal is to compute the aggregate, and then we do this pairwise masks based on the edges of the graph. Now, in a lot of these contexts, when there's questions of security and privacy, I'd also like to make this connection for those who haven't seen it. I think we looked at percolation in a lot of contexts. Often people talk about like adversaries or like nodes that you do not trust as occupying some sites in the network. So these could be a random fraction. These could also be an adversary who has maybe the global picture and tries to go for the weakest links, weakest nodes that will be most useful to it. So now suppose in this toy model, at sites 1 and 6, we had nodes that are sort of trying to de-anonymize or recover individual weights of these other nodes. And they can also potentially talk to each other. So in this, what happens actually, all of the masks that are generated with adversarial nodes are effectively useless. And in particular, I don't have a very clear picture, but what actually happens is you think of the mask, you can think of remove all of the nodes that are adversarial, look at the subgraph that remains, and that is only what is going to be having the masking. So in this process, what one would want is to design this network well enough so that even if there's some adversaries, after you remove the network, there's really no node that's like isolated, this little node on the right. It'll make all of this a little bit more concrete. But I wanted to share this application because here there is this sparsity connectivity trade-off manifesting. So if you had all the resources in the world, you just organize these nodes in a complete graph, generate as many masks as you could. But in practice, that would entail a lot more communication, like in terms of generating these masks. And imagine running this for many, many steps in something like a gradient descent algorithm for really high dimensional vectors. So one of the innovations that has come up in this area is to go from complete graphs to graphs, like regular graphs, something that could like have good connectivity, but without requiring too many edges. So there is this inherent trade-off. The catch here is we want to get a good trade-off on this while also having a way to construct the network that's easy, lightweight, can be done in a distributed way. If there's no notion of which node connects to whom, and so on. So this object actually, I'll say like how recent like works in this more applied context. Use a model like this without actually, I think, realizing it's a graph that's pretty well studied. I don't know if there's an earlier reference of it, but I saw it as appearing in the 80s as the random M orientable graph. So now let me describe, and now I think the authors call it, from that paper, call it random chaos graphs. So let me describe what this is. Then, yeah.
What are these masks like typically in practice? Like what kind of mask somebody provides?
So I think there's usually like a key exchange protocol, like a Diffie-Hellman key exchange protocol, where you and I share like a cryptographic primitive. And based on that is not usually that big. And then you use that to generate a mask. And I've seen them appear in both contexts. One is like statistical noise that people add. The other is also like more cryptographic. Happy to like direct you to more. I will also cite some of those papers now. So now, just talking about the subject, I think it comes up in. I'll not be surprised if a lot of you would have seen it with another name in a more general context. But for those who haven't seen it, so this is one way of constructing a random graph. Given n, which is the number of nodes, we have just one parameter, this capital K, with aiming to make an undirected random graph. There are also variants which get to a directed random graph. But here, say, just as a toy illustration, suppose we want to generate random 2-out graph on 6 nodes. What we'll do is each node is going to select k other neighboring nodes uniformly at random from the remaining graph. Each node is going to do this, and we say there will be an edge between 2 nodes if either of them has selected the other. So this is one of the random k-out graph. One thing that is nice about this is one was, of course, there was this whole distributed construction, and it has pretty good connectivity properties. So it was well known that as long as this k parameter is 2 or more, you're going to get a graph that's connected with high probability. And then what this means for practitioners is, so in this graph, you can see the average node dB would scale roughly as 2 times this parameter. So if you were just trying to go for connectivity, just an average degree of 4 would be enough. And it's, of course, you could have done something better, like trying to just go with random regular graphs, but say compared to often when people use Erda Srini, this is pretty good because you don't have the average degree scaling with a network size. So one of the first things we did when we started looking at this object, so our motivation throughout was trying to see in a lot of practical context, people were trying to decide how to choose these parameters to get, say, this stamp of connectivity, and that would translate to certain privacy guarantees. So we used the framework in our paper and we extended it with some other bounds to derive finite n upper and lower bounds on this connectivity. And then asymptotically, we showed that this is order-wise optimal. Okay, so far so good. I will go back to the application in a bit, but just bear with me. So the random chaos graph was a pretty good object to consider when you wanted connectivity in a distributed context without expending too many edges. Moreover, I've not talked about it, but it also has certain other connectivity properties that will answer some of the questions that we began with. And then and again, there were people started, I think, in the random graphs literature also. I think sometimes these objects appear. I've seen it appear as random digraph, but I think it can mean a lot of different things in different contexts. But one simple question to ask is, what if there is a small fraction of nodes which did not make these two selections? And would you still have as good as connectivity and like other properties? So this is the other object I'll talk about. And in an applied context, if some of these edges or masks fail, you want to be able to study what will be the result on the connectivity and other notions of it and so on. So this is just the simplest extension. Consider that each node is endowed with a type. With a coin toss, you assign it to be a type 1 or type 2. We assume this is a constant that's strictly positive, doesn't scale with n. And then based on this, you have a similar procedure. So suppose here the blue nodes were called type 1. They just select one other node. The red nodes are called type 2, and they select, in this picture, 3 nodes. Similar way, you construct a graph. There is an edge between 2 nodes if either of them is selected. So now I'm going to switch. So I've introduced the broad motivation. I've introduced the specific random graph model. Now I will make a little bit of a more concrete connection between, in those contexts, some properties that would matter. Yeah. Okay.
I also want to add a question on the model. So the edge exists if node I selects node J, and that's regardless of the type, right?
Yeah.
In type independent edges.
Yes, yes. Okay. Thanks for that question. Yeah. Okay. So now I'm switching back to the more applied context. I do want to, so there's actually so at the time when I was doing my PhD, I was also affiliated with the Privacy and Security Institute. And this model, whatever you would like to call it, was appearing in sort of disguise in a lot of these settings. And often what practitioners would do is try to take an order Srini graph with the same average degree and try to say how should we set the parameters. So there's all of these applications, I can talk about them. But this is one application that this one I talked about a little bit briefly. Okay. So let me first fully tie this. So some of the questions that are interesting now. So I already showed you there could be, in this setting, their edges are masks, and then there could be some sites that are occupied by adversaries. You would want to ensure at the time of designing this network, if you know a priori how many adversaries you might have, how could you ensure that even when they are present, that your network is connected? So, and I like to think about this in two contexts. So one is like a very powerful adversary, which can like occupy the sites, whatever sites would give it the most information. The other is maybe more like the percolation case, where you could have like either a random subset of nodes or with an independent probability, you can have an adversary occupying the nodes. And then I thought, like, at least for the targeted subset of nodes, what one could use is the property of k-vertex connectivity. And I will make that concrete in a bit. But just when we are at this layer of applications, I want to make this interesting connection. I think it was something I realized while working on this model and talking to all of these different contexts. This is actually something called secure aggregation. This is paper from authors, I think, at Google Research. So I was now talking about starting with this communication graph. So in their context, it's often what is known as federated learning. So the graph is a little bit more abstract. So you have a server that can facilitate your communication, but these edges actually, there are ways to generate mask. So it's like a virtual graph, but the idea is similar. And in these contexts, if you see like the exact same graph is constructed as follows, each client is making so many selections from other nodes. You have an edge if either they choose them or you choose them. And and somehow there wasn't a good characterization of how, if you were giving a certificate of privacy guarantees, how would you handle different adversarial models? So that was a nice connection, I think, that I realized. I'm also aware that I've spent a lot of time on the context. But now let me just dive in. I think for this the audience in this room, this is maybe like a very familiar slide. But one way of thinking about connectivity, especially from a more practical lens, is going from like something like a weaker to a stronger notion of connectivity. So one connectivity we already spoke about, and if I let C max denote my largest subgraph, so it's essentially saying that's all of your network. So one object I've looked at a lot is K connectivity. There's different, so there's K vertex connectivity, K edge connectivity, and so on. But we'll mostly talk about K vertex connectivity, and what it does is it ensures that your network stays connected despite any K-1 node failures. They could be anywhere in the network. So it's sort of like then a worst case attack mode. And then, but sometimes in practice, you may not really be able to generate a network that has so many edges or has so many masks. So it's often also useful to characterize the largest component size. And in particular, actually, ideally, if we could characterize the distribution over all components, that will be even better. I'll talk about that in the end on the chalkboard, but these are some ways of thinking about it. So, okay. So in these contexts, one way to think about what properties might matter, this is by no means like an exhaustive characterization, is to say, okay, so we had the most vanilla, I'm calling it homogeneous random K-out graph. And suppose, like, let us not make this K something like that's finite. Let us in general allow it to scale with the number of nodes in the network. Then we introduced this object, which was very one simple way to introduce some inhomogeneity, where you have each node be assigned to a type. And then based on the type, it determines how many selections it makes. We considered the simplest case, where there is, with a strictly positive probability mu, a node that makes just nodes that make just one selection, and the remaining can make number of selections Kn that scale with the number of nodes in the network. I apologize with the overloaded K. So there's little k for the K connectivity, capital K for the K out graphs. But since these were the definitions for these objects, I stuck to them. Okay. So I already talked about this result, which said that for the homogeneous random K out graph, these two Kn actually didn't have to scale with n, 2 was enough. And then moreover, there were results in the same paper which said that if you wanted K connectivity, which was, say, if you had 5 connectivity, means your network is going to be fine in terms of connectivity. You can take off any 4 vertices you want, but it's going to be fine as long as you set this parameter to 2 times this little k value. So there was work showing that the moment you introduce some inhomogeneity in this model, so if you have, there is for each node a strictly positive probability of it picking less than 2 nodes, then you have the remaining nodes, if there were just 2 types, they have to have a Kn that grows unboundedly with the number of nodes. And then some of the questions which we looked at were, one, so this is something I already showed, like whenever possible, can we give something that holds for a finite number of nodes? Then what if there are different modes of attacks, either captured through K connectivity or like a random subset of nodes? And this is I want to also make a note that this is an object, even referring back to Ganesh's open problem talk. So he talked about, I think he mentioned D out graphs. That was a bipartite version of the random K out graph. And there are many other variants that are studied. Some of these I'll talk about towards in the last maybe 10 minutes on the chalkboard. Okay. So what are some of the results? I think, so what we tried to do was, so for this property in particular, we derived a 0-1 law. I'll talk about how we came to it. For the homogeneous K-out graph itself, what we tried to look at is if you have different subset of nodes that fail, when the subset of nodes that fail, what can you say? I think this would be square root of n. But how should you scale K so that you are guaranteed to have either one connectivity or a largest connected component greater than a certain threshold? And we've done this for different regimes. I'm happy to direct you to references on this. And then I will just spend a minute talking about, I also want to talk about this because I think when I was like looking at this object, I really used like the very basic method of moments type of approach. Like I'm curious if, as you see, like the arguments, if you think this object could, and this property could be handled with some other, I think, clever way. So this is sort of the result we had for K vertex connectivity on this extended sort of random K-out graph, where there is a parameter in addition to Kn, there's a parameter mu. A node with probability mu just makes one selection, and then with otherwise it makes Kn selections. So this is sort of the threshold we got. We didn't characterize what's happening between 0 and 1. And this is just like an empirical sort of illustration with finite nodes. So I'd given this talk to an engineering audience, so this might be redundant for a lot of you in the room. So essentially used method of moments. I think it's like one of the most basic things one can do when dealing with combinatorial objects. So I will not go over this, but I will just say that the most challenging part for this model tended to be dealing with this one law, in particular with sending all of these limits appropriately. And as you can see in this graph generation mechanism, there's correlations between presence of edges between nodes. And even more with this mode of inhomogeneity that we introduced, if you make an edge, you expanded an edge, but it could also potentially make you more likely to be of the type that makes more edges. So yeah, so just going to very quickly show like how we thought about it. I would be very keen to see if like some of the tools and concepts we've learned, I think, over the week. Yeah.
So for this random K-out graphs, so in the previous works, was K ever random or?
So in a lot of the work by Alan Fries, K is often fixed.
Okay.
So one of the other papers I had, in that what they looked at was it was a directed, more general version of it, where K could be sampled from a distribution. And I think they were trying to see for the directed version of that, what happens to the component size.
So your K can also be thought of as a random K, right? So if you look at the annealed law, but are you fixing the type 1 and type 2s first and then doing this, or?
Yes.
Okay.
So I think for me, one also like curious question is, so my guess is if the property we were going for was the largest connected component, there would be a lot of results already. Like I'm not sure how, if we are looking for something like, for instance, K vertex connectivity, how some of those would apply. And I will try to save some time and I can go to some of the questions I have in mind for, I think, especially being in this audience. Okay, so this is just saying that even if you had a connected network, the minimum node degree and K vertex connectivity are not the same properties. Minimum node degree often is easier to reason about, but then doesn't guarantee K vertex connectivity for free. In particular, in this graph, you are connected. All nodes have a minimum node degree of 4, but you do not have K vertex connectivity. So how we reasoned about this? We just first argued about the minimum node degree and got it phase transition. To the room, I'm also curious if there are like more general results which say that if you've established a law for minimum node degree, can you always guarantee that there will be K connectivity following the same threshold? So that is that okay is okay, but in general for a larger K, like I am not sure, and especially for a model like this, but like that would be very, very cool because we got the same threshold for K vertex connectivity. And how we did was essentially, so the minimum node degrees, one of the laws automatically, so if you do not have a minimum node degree, at least little K, you're not getting K vertex connectivity. But for the other direction, I think we did again something like super first principles. We tried to see, so if we already established the result, so delta is your minimum node degree for it, but then could you say, like use this to show a result on the K vertex connectivity? And then what we tried to see is look at this event of having a K vertex connectivity at least K as this difference between the minimum node degree being k and then the minimum node degree being k, but the vertex connectivity being less than k, and sort of defining simpler and simpler events. And then ultimately we landed at this situation where there is a vertex cut that fragments the graph and it's of size L. And like in the interest of time, I will not talk about it, but this is how we reasoned about using a result for minimum node degree that we derived to take it to k vertex connectivity. Okay, so I will summarize this, but I really want to take some time to think, to sort of have some problems that are really important in practical context. But just to summarize this, so what I talked about and hopefully motivated enough is distributed network design. Balancing sparsity with connectivity is pretty important. So there are obvious implications like being able to communicate and some indirect implications like privacy mechanisms. So random k-out graphs was an object that in these applied contexts was appearing over and over again without necessarily being attributed as being that model. Often practitioners were using Gaussian graphs to approximate them. Yeah, so this is something, and it's really I did not talk about it, but even like in cryptocurrency networks, people like anonymity preserving routing use something like that. So it's systems that are decentralized with limited trust, often this comes up a lot. So we tried to characterize properties in different operational contexts, albeit it wasn't exhaustive. This final bit I would like to do on the chalkboard. I'm almost out of time. Okay, this I will not speak about, but what I realized, I was thinking about these objects for so long when I started reasoning about these probabilistic graphical models. The way they define independence is actually a lot like connectivity. So I'm happy to chat more about this. So this is more about distribution learning, and here also combinatorial structure comes in. But I will skip this. And I really like this as a motivation for me. I think our world is so complex. I always feel like a network perspective brings in a lot of insight. I'm planning to be here between 4 to 7. My jet lag is finally gone to chat more. I do want to spend some few very rapid minutes on the chalkboard to talk about, I think, some properties that would be interesting to consider. So I have about 5 minutes, right? Okay, awesome. So sorry for the abrupt transition, but I was really excited because these are some properties I've been thinking about, and I feel this community might have answers. So just first was this whole context that I was talking about. You have a graph, say it's made with the construction similar to what I defined. You have certain number of sites that are effectively removed, and then the edges corresponding to them don't matter. So then it would be really nice if we could have for this. So this is just, I'm calling this. So what ends up happening in the graph that remains, you actually in those algorithms get partial sums. So if your h and k was the object you began with, and there was, say, a fixed number of deletions, or you could even think of this as a fixed fraction, could you characterize distribution of component sizes or some approximation of? Because these sizes actually have like connections with partial sums that are revealed, and I think it would be really cool. One more thing, I think that so far, I think isn't some.
Mansi, these deletions are known, like how many you delete? You have this number, like...
I think the way you'll think of this is, if I'm designing this method, I will take a budget of what is the adversary's power. And that will be an assumption you will work with to begin with. You could be conservative to begin with, but that's how usually. And often it's very much related to like fractions that, so like I think percolation and all those things would be useful there. The second thing is, I think it touches upon some, like I think for instance, some of the objects we've looked at. So I did not talk about, I think, physical proximity or geometry at all. So I think, so there's already some work, I think, by Alan Fries, which talks about random layout of graphs, of large graphs. So here, essentially, instead of making your selections uniformly at random from all the other remaining nodes, you begin with a graph that constrains how you can make selections. I don't think all of the properties are well understood here. The other thing is, this is maybe like I think Nelly gave a talk on random geometric graphs. One thing I feel, I don't know how much it is studied, but if one could sort of take the random layout graph and then remove all the edges that were not between nodes that are proximate enough, like say for instance, by using the random geometric graph, what can you say? I think that will be another thing that would be interesting. Also, nodes that come in later. So if you already had a graph and there were nodes coming in later, how could you think about what mechanisms you could use? One thing I think, since that was also like proximate to a talk we had in the morning, I don't know how to deal with this, but if one could give the spectral properties in particular, or any approximation of it, of the second smallest eigenvalue of the normalized Laplacian, I think that will be very nice because it often relates to convergence of many, many runs of algorithms that are happening on this. I'll now make it really quick. So there wasn't an exhaustive characterization we did. So there's homogeneous, there could be inhomogeneous with like Rajat mentioned, or Shayan mentioned, like a distribution. And then you want to characterize all notions of connectivity to the best possible way, while saying if you could have like finite n bounds whenever possible, and deal with deletions.
A little bigger, we can't see from so far. A little bigger. Font size, yeah.
Let me read it out. So in this context, I with that. And I think finally, I'd like to say that, okay, so this is fine. And I think in the interest of time, I will conclude here. I'd also just like to say that I feel often in a lot of contexts in AI, where there's AI infrastructure, the network structure is really important. But often what I see practitioners, this will complete this sentence, test their algorithms on is either something like Doshlini or cycle graphs. I feel if we could visualize and like communicate like all of the different models there are, especially like I think both of these models I feel as well, and what all properties we can characterize, I think that will be really cool. But I think thank you. I am out of time, but thank you so much.
Questions, comments? Kumarji.
So, any study on covert time on random K, I mean, conditional that it is connected.
Sorry?
Conditional that it is connected. I mean, it was random K out graph, conditional that it is connected. Any study on covert time on it?
Any study on?
Covert time.
I am not sure. I am not sure. That will be interesting.
For random regular graphs, there are some results on K connectivity. I think the degree and K need to be the same,
Possibly.
or maybe plus or minus 1.
Sounds good.
Okay.
Like one thing I'm curious about, it feels like this object is trying to get at random regular, but it's not quite there. Like how far these results are from, because it becomes, I think, complicated to analyze when there's so much rich literature for this. So I don't know if one could use.
That's a problem. Yeah, I know that there are lots of papers also trying to characterize different properties of random graphs in terms of the minimal degree. So the minimum degree 2 is, I think, Hamiltonicity or something like that. So there are some works. I'm not sure whether this also applies to connectivity, for example.
Thank
There is also work on using where geometry is involved, in the sense that if you connect to k nearest neighbors, then when k is like log n, then it's strongly connected in the directed setting.
I think it's the K out nearest neighbor. Is that the one?
Right.
Okay.
Any further questions? There is one extremely behind. I have to run too far. Shiva.
So I think about the last bit that you mentioned at the very end for the random regular graphs, and especially about the AI server infrastructure. I think there is work in terms of random regular graphs being used for something like that, or certain optimality properties by Tsitsiklis, and very recently maybe that's something that might be interesting to look at. And yeah, that's just something I want to point out.
So yeah, that sounds very interesting. I'd love to learn.
Any further comments? Okay, if not, let's thank Mansi